morning, Mathotaarachchi. Another beautiful day that we are doing, organic chemistry. Last week we did up to question number 28 up to here. So today we are starting from here. Question number 28, part B. Okay, how do you learn how to study organic chemistry? Organic chemistry is really, really easier. And in your papers, you are in your third day today, paper part, couple of modules, couple of 3 or 4 days, you are finishing organic chemistry. So have a determination before ending organic chemistry classified, you can have a full knowledge, complete knowledge that you can convince yourself. I don't want any other support. I'm already full with organic chemistry. For that, you're going to keep remember these equations or the equation and go through the not the spider diagram, go to the short note that I have given, identification test, mechanism information, acidity basicity, those whatever in that short note is really, really important. And this spider diagram just make an imprint. I keep saying this whenever you started your theory. Keep that imprint that whatever these 21 boxes in your mind. So whenever you need the knowledge, you can get up. And also when you are doing whatever these conversions, you better to write all the methods, which is for the final exam. We know what sort of a method they will use. If they restrict everything, they give a couple of pages and also they give this kind of a diagram. So we have to just fix everything into this diagram. For that, you're supposed to know all the different methods and all the reagents and all the items. And the other statement, because the laboratory students, they are having some issues coming on this Wednesday, they have school stuff and everything. Then even other students also requested that they want to come to this the Monday class. So the Wednesday class is not conducting only for this day because you guys came on. Right. So let's start then. Part B of question number 28. Show how we would synthesize this this. They are only asking this. Okay, so initial compound not given. Are they expecting us to use these reagents? Are they giving proper reagents? Yeah, both A and B supposed to go with these given reagents. Okay, this is the reagent set that they have given. 2851. Same set of reagents that we did last week. From those reagents, again, they want us to go with this. If we analyze this compound, these two can be break from this CH2NH so that this part, this actually is a secondary amine. So this part, if you separate, this is aniline. And the other side, then you have this. With this bromine is orthoparadirector, CH2 is orthoparadirector, but with respect to each other, this connection is meta. So that first we have to convert this given toluene, this is they have given, to something meta. Then we can join this bromine. Then we are moving on to joining this NH2 group with aniline. Okay. So you're going to choose reagent from the given list. So I can join I can join this aniline later, but before that I'm joining this one because if I leave joining this one later, this can replace this hydrogen atom. And since they have given the told I'm starting that, converting this into, anyway, I have to convert this into something that which can connect with this aniline as well. And also at the same time, I will join this bromine to metal position. So I'm oxidizing this. Whenever you are writing these reagents, you can write reagents the way they are given. You cannot just write H plus KMnO4. So you're going to lose a couple of marks for this. This time they have specifically given this acid. Then I oxidize CH3 to COOH. To that, FeBr to Br2. So to metal position, now I'm joining bromine. Then there are two ways that you can go. I'll show both. First thing, I'm just converting this COOH to adding PCl5 COCl. So I'm converting this OH to Cl. And to this, I can add aniline directly. So you can make this amide. Then reducing that amide with water. So you can make this. Or otherwise, the second method, after you come here, first, you can reduce this using lithium aluminum iodide and water. You can reduce this COOH to this pink color CH2OH. To that, you can add PCl5. So you are converting this OH to Cl. Then to this, if you add this aniline, you are directly coming, making this one. Okay. Two different methods I'm showing. First method is this normal part. The second part I'm going with this pink color. I want you guys to write everything. And here, this is an aryl halide. Okay, that doesn't happen. This is an aryl halide. Once you make this one, there is no reaction between that aniline and this bromine. That I'm explaining here. Aryl halides do not react with NH3 or whatever NH2 since no F10 because its F percentage is high and also it has this resonance stability. So this bromine does not react with this NH2. Clear that. Keep everything in your mind and copy starting from here. I'm showing this Sinhala because it's here. Okay, with the given reagents, we cannot go with other methods. But there are a couple of other methods that we can use. Yashika, that organic knot is with me now. Next week you can have it. Finish. All right. Okay, they were not given these methods for that exam, but maybe for our exam, they may find some other methods. So first, BR3 bromine, then addition of magnesium bromide, then addition of one carbon, even you can add CO2. Then you are directly making this CH2OH. Then you can oxidize COOH. Different methods that students are doing. I know this is longer method, but some students rather just coming from here to here easily, they are doing this kind of method as well. Anyway, you can make this benzoic acid this way as well. Then to that, addition of this bromine, then addition of NH2, that's aniline. Then reducing with lithium aluminum hydride, you can get here. Or otherwise, FeCl3 Br2 bromine. Then the scan is that I have shown, but here again you can use this little part as well. So if you feel like you want to write this, just copy this down. Copy this down because I know some ones. Okay, after I sent you last week recording. almost of these same methods. Finish. All right. Question number 29. Part A. Just empirical formula. C6H8 NCl. C6H8 NCl. Check your answer if you've done something. Method is extremely easy, so I'm not wasting time on that. A is soluble in water and the solution is acidic. So whatever we don't know what is this A, they say it's acidic. Aqueous solution contain 1.3 grams of A required this CV. This CV titrate using phenolphthalein as the indicator, determine this 1 mole of A reacts 1 mole of sodium hydroxide. They want to find out the relative mole mass of A. Empirical formula is known. So A is to sodium hydroxide. A is to sodium hydroxide is 1:1. And so that same number of moles of sodium hydroxide is supposed to react with same number of moles of A. CV of sodium hydroxide given 0.4 into 25. 0.4 into 25 into 10 power minus 3 mole equals 0.01 mole. Since the ratio is 1:1, same number of moles of A is producing, and this number of moles contained in this mass. They are giving the mass is 1.3. So mole mass equals mass divided by number of moles. Mass is 1.3, number of moles is 0.01. So that mole mass is 130 grams per mole. Then they want us to find this molecular formula, and we already know the empirical formula to the power n into n equals 130. But the mole mass of empirical formula equals 129.5. It simply means n is almost equals to 1. So that same structure is the molecular formula. Okay, up to here, or check your answers up to here. All right, everybody finished because students in front of me, they have done this. Then A undergoes the following reactions. Aqueous sodium nitrate, sodium nitrite 0 to 5 degrees Celsius. Something is happening, and at the same low temperature, addition of phenol gives with sodium hydroxide, the basic medium, it gives C. Further, an aqueous solution of A gives a white precipitate with silver nitrate solution. White precipitate with silver nitrate means they are supposed to be ionic chloride. Ionic chlorides. Know how we are doing question number 29. they want us to find this A, B, and C. Okay, this is the molecular formula. Just looking at this, it is showing it is highly unsaturated. So it's highly unsaturated. So I'm gonna subtract benzene part. So the remaining become NH3Cl. So I have this C6H5. I have joined this nitrogen. Then just to join this hydrogen, you have only this nitrogen and chlorine. So either you can write NH2 plus HCl, but A is a one single compound. So addition of this HCl to NH2 making NH3 plus Cl minus. So the initial compound, so that is NH3Cl, and this is directly acting as aniline plus HCl. This is acting as NH2 plus HCl. To neutralize this here, I need this sodium hydroxide has here. Sorry, that is a mistake. We already have HCl, so just adding sodium nitrate is making this HNO2. That HNO2 with low temperature is converting to diazonium. And to that, if we add phenol, this hydrogen at the para position, this para position hydrogen gets away through the electrophilic substitution. This is joining with this nitrogen, releasing HCl. So you are making this diazonium, so which is orange color. All right, copy this, whatever on this. Anything that any hint you feel like writing, you just have to write that. And here it's the marks, just put here plus and minus. This is not necessary, but still we know that this is also ionic plus and minus. And for your knowledge, this is orange color dye. This is orange dye. Okay. You can study faculties too, so I'm going with this Sinhala and let me get this clearer. So they have given these reagents. Anyway, I go with this one. Just remember, there are only two methods that you can join this R groups to benzene ring. Friedel-Crafts alkylation or Friedel-Crafts acylation. CH2, connection carbon. Is it straight to that? No, they are just coming in. Then this part is separately. This is again, you can go with Friedel-Crafts alkylation or acylation, but let's see. At the same time, you have OH2. And also, with this one is orthopera, this is also orthopera, but the connection between these two are metal. Keep that everything in mind. I'm going to highlight the reagent. This, I think I have it here for your paper as presentation. Annotation list. For iron, is it iron or did I write that FeBr3 on here? Is it iron or iron or ferrichromite? Ferrichromite. This iron. Yeah, just maybe because for name because we are not making iron, it is FeBr3, okay? But it's just we can go with that. And they want to start with this with benzene. Other than benzene, we need to join these two groups. For that, they have given only other compounds with this carbon or organic compound. This is acetone, but it has 3 carbon. We don't want 3 carbon. We are not joining 3 carbon because this is 2 carbon and this is again 2 carbon. The other two they have given is this acetyl chloride that we can go with Friedel-Crafts acylation. And the other thing they have given is this ethanol. Alright. So very easily we can join this with this. And then we can reduce this using, yes, this is aluminum hydride is there to convert this into alcohol. And they are also given, they have given this dill H2SO4. See, but still we have to consider this as H2SO4 because there are no other methods that we can follow to convert this alcohol into this double bond. We have to convert this alcohol to double bond, but for that they were not given this H2SO, but still we have to go with that. And then joining for this other group, what I can do. I can do it green now because there are no any other methods that I can derive this group to meta position. What happens if I go with this again? COCH3. If I just another, let's say, after converting this, if I, I can go with again with Friedel-Crafts acylation, but then steps are increasing. I have to add everything within this given format. 1, 2, 3, 4, 5. I have to complete this conversion only using 5 intermediate. So I cannot join here again this Friedel-Crafts acylation, that's COR. So this is the method I'm using. Let me explain first, then I'll give you guys time to write there. I know almost all of you have taken the right answer, but still, I'm just showing you guys the thinking style. So initially, they want us to start from benzene. From benzene, I'm making Friedel-Crafts acylation. So CH3COCl and aluminum chloride. So this is meta director. At the same time, so I'm joining this bromine because now I have the idea of this green iron. I'm just leaving bromine additive. Now I'm converting this COCH2 to this. How do I do that? I reduce this with lithium aluminum hydride. Then I supposed to add this constituents of 170. They were not given that. So you cannot write that. You have to use from the list. This is from the list. This is for your knowledge. I have written this separately. Here I am using a different color. When we are converting this OH and H gets away, I'm just converting this CHOH double bonded. And then magnesium triether doesn't do anything with alkene. This is alkene. So then addition of this carbonyl, what happens is this benzene is joining onto this carbon. polarizing this oxygen here. So this carbon is this carbon. This oxygen becomes OH. This CH3 already was here. So this carbon, so this carbon, the larger part is joining. Is this clear? Could you get the answer? Did. Very good. All right, whatever you can get from here, right here. Or with the main conversion, then I'll show these parts again. I don't remember these. Are you ready? I finish. Okay, see. If you guys done this mistake, that's why things we are doing online and doing everything. So after addition of city value hydride come here. But if we add bromine now, bromine can join to all these positions because it is being activated. It's not going to metal. And also, let's say that you want to join the second group here. Let's say you are joining another that is going here. But then whatever we are doing, it is happening to both CO, CH3. So you cannot get two different CH2 double CH double CH2 here and CHOH CH3 here. So we are not doing this kind of. you want to write something from this, just come there down. You're not clear. You're not clear. Yes, we have this commercial translation. Kenapa grafiknya ini apa sih? Tony, are you okay? Oke. Lagi ini. Kamu lagi kan ini? Nih. Ini. Alright. Yeah, yeah, it's today. Okay, sorry guys. I guess you guys are dealing with this. Moving on to question number 30. Again, they are given this set of reagents. You guys have these reagents, so I'm going with this Sinhala one. This, I want to rewrite the English one again. I have read the Sinhala one, it was awful. Okay, so they started from benzene, and the final compound is given. So these are the reagents. They have given this conc engine HCl, sulfuric, nitric, sodium hydroxide, sodium nitrite, CuBr, Br2, CBr3, PBr3, lithium, aluminum hydride, and tin. Okay, if we analyze initial and final, all right, starting from benzene, they are coming to something middle. From that middle thing, they are making two different compounds. Addition of these two different compounds are having this. If you forget this two bromine, this is the reaction between what? Diazonium and phenol. Then one side they are making phenol, the other side they are making diazonium from a common precursor, and that precursor also have with respect to this nitrogen, this is meta, And also with respect to this oxygen, this is also meta. So in both this common one, there are supposed to be this meta bromo position. In meta position, there is supposed to be this bromine. And we can make both these by diazonium. Okay, by aniline. Aniline, low temperature going to diazonium. Aniline, normal temperature going to phenol. Okay, that is the part they have done. So here, this compound supposed to be this NH2 or aniline. This, if you forget this one, this can be this NH2. Okay, either this or this both are correct. All right. So here I'm making this. Here I need to make this compound. Let's say I need to make this compound 1 NH2 here bromine. From benzene, making the aniline, one single plant, that is, we are making this nitrobenzene, and that they have even given zinc. So zinc concatenates sodium hydroxide, then you are coming to here. With excess sodium hydroxide, you are going there, that's also correct. So either this one or this one are correct. Okay, what we are doing is, compliant pump sulfuric, 50 degrees Celsius, we are coming to this meta position. Sorry, nitrobenzene. Nitro is the meta director, so that when we are adding FeBr to Br2, it is joining this bromine to meta position with respect to this NO2 position. To that, now I'm going to convert this NO2 to NH2 or NH3 plus 3 minus. Tin concatenates sodium hydroxide, I'm coming here to that. Sodium nitrate gelates here, low temperature. 0 to 5 degrees Celsius, you are making the aniline. Sorry, you are making the diazonium. If the temperature is above 5, the normal temperature, you are making the same sodium nitrate gelates here. So you are converting this to OH. And okay, now you have this is the first condition that you are coming across with this kind of situation. This is all right. With this one, whatever the hydrogen here is joining with this nitrogen, releasing HCl. So this side is all right, no problem. But this side, how do you know to which position next group is joining? Okay, with respect to bromine, here I'll go with blue, ortho, and para. Then with respect to phenol, O2 and para. But so this position is so that activating by both. One thing. The other thing is this phenol is more prominent because that is the strong ring activator. This is a ring deactivator, even it's called para. So that this can go directly onto this para position. So they can make this kind of a question for MCQ. Then when you are joining, this time they have given this. So you can just get the answer. Even if they're not given that, just remember. So this fluorine gets away with this hydrogen joining here and making this one like this. All right, this one is this little one. All right. Okay, copy. She's always so good. I don't know whether she's skinny, but she never gets careful with anything. Tute. Makes you feel like I don't need it. Okay, Jani, Zara, it's really okay. It's really okay, Jani. Just don't worry. Whenever you feel like you want to come, just come. I know it's not your problem. No, it's not your fault. Don't worry. Finish. I think to be honest, or not all, you will do it. Since almost all these students are here, and others I know they are getting this recording as well. I decided to do like this. When we are done with, I don't know, you guys tell me your idea. Once we're done with classified, we are making full papers. We need more time for that. I'm going to explain everything very slowly this time. So that 4 hours may not enough. So what I'm going to do is, I'm doing Monday and Wednesday for each week. It's up to you, tell me. You are paying only for 1 day. You are not paying for both days. Per week, you are paying only 1 day, okay? So we start this paper with this discussion on Monday. If we have to continue on Wednesday, we are continuing to Wednesday. Just let me know if you guys are comfortable with that. So you are doing 2 classes with me on Monday and on Wednesday. Only if you guys feel like you want more expression for this full paper. And the other thing is you guys have to find another day to come and sit for the paper. Whenever it's possible, when I'm giving time from that time. So Salam students, what they can do is, if possible, they can come evening on Monday. Because I have classes on the evening Monday. Sinhala, are you free Monday evening? No? Otherwise, what you can do is, one couple of days you can come here, you can practice with me, so you can do full papers at home, and bring in the paper with me, but I don't recommend that. Because these classrooms are saying, when you are sitting here as an exam, you feel more than the exam. You are working straight 20 hours, at home you are getting disturbed and so on. So try maximum just to get here at least once a week to sit for the exam. I'm not giving these rules, I'm just saying, okay? All right, I think you guys are done with this question. So we are moving to question number 31. An industrial important organic compound contain carbon, hydrogen, and oxygen. They want us to write the balance equation. That you guys have done this already. So CH, so X amount of carbon, so X CO2 Y amount of hydrogen, but we have H2. So we divide Y by 2. Then oxygen becomes 2X plus Y divided by 2, amount of yeah, but since I have already started to explain this algorithm. Sorry, yeah, I didn't see that. There is another part of 30. Question number 30. Then we are getting 2x plus y divided by 2. At the same time, we have z here. Then minus z. At the same time, we have this O2 here. O2 here. So that you are dividing everything by 2. Then I multiply the whole equation by 2. 2 here, 2 here, 2 here, and 2 here. These two are cancelling off. So that the answer is this, or even this is correct. All these answers are correct. Anyway, let me go with the 34, 25. Yeah, I'll explain that part again. Okay, so this is the answer. And let me explain the second part as well. The combustion of 62 grams of X. Okay, 62 milligrams of X gives 88 milligrams of CO2, 54 milligrams of H2O. So we can just forget that milligram part because it's same for everything. Then I have to divide this each of, okay, then 62 is to 88 is to 54. So to get the molar formula, molar ratio, I have to divide this by the molar mass of each of these, 62, 44, and 18. Then the ratio become 1 is to 2 is to 3. So that I'm going to go back to this 2 and 1 matching. 2x and 2 is matching. Y and 3 is matching. So I'm going to go with these trigonometric ratios with these more ratios so that I can write this 2 and this 2x with this 1 and 2. So I can write 2 over 2x equals 1 over 2. So x equals to 2. Then 2x and y with 2 and 3. Then 2x is divided by y equals 2 over 3. X equals to 2. So that y equals to 6. Then 2 carbon, 6 hydrogen, and OZ together equals molar mass is 62. So that they become 2. Then, okay, copy up to here. I'll show the last part separately. I'll go back to part 3, part B later. This is a wholly different from the working. Okay, finish. The reaction of 62 milligrams of X with sodium gives two. No, let's finish this. The reaction of 62 milligram of X, this is the same question, that's right. To gives 2 milligrams of hydrogen gas. Okay, 62 milligrams of X gives 2 milligrams of hydrogen. Okay, so molar mass of this we already we can calculate, but also they have given that. It's not clear. About this one. Okay, X is 2 hydrogen, 62 milligrams of this, giving 2 milligrams of this. I divide each by molar mass of X and molar mass of hydrogen. Then the mole ratio is 1:1. So 1 mole of X reacting with 1 mole of H2. How do you get this hydrogen? To get hydrogen, they are supposed to be OH. And how many OH? This is supposed to be the reaction. This is the reaction. So to get 1 H2, they are supposed to be 2 hydrogen, 2 OH. So to get 1 mole of H2, they are supposed to be 2 OH groups in X. So that they are supposed to be 2 OH. Then the given structure has 1 carbon, 2 carbon. And 1 OH, another OH, then 4 hydrogen, 2 hydrogen already gone, 4 hydrogen, 1, 2, 3, 4. You can draw this structure as well. All these are hydrogen, 1 OH, 2 OH. But obviously, 2 OH coming to 1 carbon is 1 carbon makes it unstable because these oxygen are very electronegative. So that structure is supposed to be this. Clear that? Okay, copy that. Just write here, 2 OH groups needed to get 1 mole of H2 from 1 mole of X. 2 OH groups needed, I'm just reading this Sinhala part. 2 OH groups needed to get 1 mole of H2 from 1 mole of X. From 1 mole of X, 2 OH groups needed to get 1 mole of H2 from 1 mole of X. Okay, then the last little part, an optical active compound C6H12O gives a yellow precipitate with 2,4-dinitrophenyl hydrazine. Just underline that. Yellow precipitate with 2,4-dinitrophenyl hydrazine means it's supposed to have this carbonyl part. Underline that and write there carbonyl. Not react with ammonical silver nitrate. Underline that. Not react with. Ammonical silver nitrate is tolerant. It simply means no CHO aldehyde. No CHO aldehyde. No CHO aldehyde. All right, this is the part I'm using. So there's supposed to be this ketone group. Usually what you can do is you can write what is even functional group first, or you can start from the smallest one. Here I'm starting from the smallest one. Here purple color numbers are steps that I have followed. Okay, the very first step is just putting the smaller hydrogen. Then I'm joining next small, that is 1 carbon. Then I'm joining next small, that is 2 carbon. The next part, since I have gone with 1, 2, 3 for another 2 carbon remaining, so I'm just joining that 2 carbon. But in my mind, I know there is supposed to be this ketonic part to make the ketone. If this is aldehyde, you are putting COH here. But they are saying it's not giving this silver nitrate, whatever the thing, silver mirror. So it's not an aldehyde, and so it's that, so that is supposed to be a ketone. So you have to put this double bonded oxygen onto this middle carbon. So that this is the kind of carbon, and this is the structure. Moving on to question number 30, part B. Okay. 2 carbon, 2, 3 carbon, chain extension by 1 carbon. Easiest way of chain extension with 1 carbon is going with HCN or KCN. But it's not given, but they have given this 1 carbon formaldehyde. So we are going with Grignard with formaldehyde. Joining of any carbon into another, 2 methods, but either Grignard or the other method is aldol. From aldol we cannot add 1 carbon here because they are not given this reagent as well. If you add aldol from this one, you're going to get 4 carbon compound. So we are going with this carbonyl. Carbonyl is supposed to join with Grignard. It simply means we have to convert this ethanol to Grignard. So that I'm adding first this halogen by PbI3. Then I convert this using magnesium and dry ether. I'm converting this into Grignard. To that I'm adding formaldehyde and water. And then it is making this OH, this compound. What happened here is HCOH. And to this negatively charged this carbon is attacking here. So this is joining here at CH2, CH3. So that you're going to get CH3, CH2, CH2, OH, CH3, CH2, CH2, OH. See, now you have to be able to play these reactions. We earlier learned the reactions, now we are playing with them. But still we need to join this, so we need to go to this triple bond. I'm joining to bromine. For that I need a double bond. Concave is 170, but the temperature is not given. You don't have to write this, they were not given. Then addition of bromine, we are making these two. Alcoholic KOH heating, remove this HBr to HBr, making the triple bond. So it is. Just feel free to ask any question you have. Moving on. Question number 32. Draw the structure of 2-methylpropene. So the double bond is supposed to be there. This is the answer. Draw in the box P and Q respectively the structure of the major and minor products when HBr addition to this compound. So that's with Markovnikov. They are not just saying giving any peroxide, just the Markovnikov. This is the tertiary carbocation going through this. Hydrogen goes to the hydrogen is high. So that this is the major product and this is the minor product. Bromine goes here for the minor product. Then they ask of the mechanism. So this is electrophilic addition normal reaction that we already know the mechanism, electrophilic addition. When we are joining, now we know with the Markovnikov rule, hydrogen goes to where hydrogen is high. So first we are joining this hydrogen onto this carbon. Then we are going through this more stable tertiary carbocation. Then plus charge supposed to come onto this carbon. Okay, this is the first time we are doing this mechanism. We choose this more stable carbocation, but it's very easy to understand. First, this Pi bonding is donating onto this hydrogen, which is already polarized. And the hydrogen is joining bromine discharge existing as Br minus. Later that Br minus is joining, attaching onto this carbocation. So this is the mechanism. Okay, I'll read this sentence once you put this. All right. Let's write this one little sentence. Form tertiary carbocation. Form tertiary carbocation get stabilizers by inductive effect. Get stabilizers by inductive effect. By inductive effect. All right, you have the question with you. I'm going to go with this Sinhala one. Here again, this compound A, molecular formula is given as CH14O, exhibits optical isomerism. Okay, there's supposed to be this chiral carbon. It reacts with acidic potassium dichromate at room temperature to give a carboxylic acid. We are using the knowledge that we have. C6H14O. I've given all these homologous series common formula. CnH2n plus 2O. That saturated alcohols or ethers, but they are reacting with potassium permanganate. So this is definitely an alcohol. But the product is carboxylic acid, alcohol, RCH2OH, OR, CHOH, R. Okay. Tertiary alcohol do not oxidize. Secondary alcohol oxidizing to, secondary alcohols are oxidizing to ketones. Primary alcohols are oxidizing to COOH, carboxylic acid. So that product is carboxylic acid, so that is a primary alcohol. Secondary alcohols give ketones. Tertiary alcohols, no oxidation. Therefore, when you are drawing, you have to show this CH2OH. You have to maintain CH2OH because it's the primary alcohol. All right. So I'm gonna go with whatever the possibility. So if I go with possibilities, I can only go with these three. I have to maintain the CH2OH. So I'm just drawing the CH2OH. Then one hydrogen, one carbon, remaining is 3 carbon. So that I can go. I'm going to keep the same, this part here. I'm changing this 3 carbon into a branch. So I'm just going to break one of these carbon and joining it one inner here. So that I'm coming into this. At the same time, I can detach one of these carbon and join it here. CH2OH. CH2OH, then the rest of this part. Okay, other than that, you cannot find any other structure. All right. Before we moving on to part 2, whatever you get these hints from this, just copy this down. Not the answer. I want you guys to get the idea how you're going to get there. Writing the answer, copying the answer, just copy this part. I definitely going to rewrite this for 2010. Not zero. Finish. Okay, so let's copy the first 3 structures. Copy these first 3 structures. And you're supposed to fill with hydrogen. You are not writing like that. Just fill with hydrogen, okay? And I'm showing the chiral carbon with blue. All right. Then rest of the parts. I'm going to go with this structure, this explanation here. Okay. Compound A when heated with concave SO4. So this is A. You can go with all 3. See, again, I have done that. That's why I'm showing this. Let's say, okay, I'm showing here. So compound A, when heated with concave SO4, compound B, molecular formula C6H12. C6H12 means alkene. So you're just, I'm just from this one. I'm just writing this expandable this structure, my straight chain here, okay? Same thing. Then this OH gets rid with this hydrogen. This is the side chain. So I'm coming to this. You guys know this. From this OH again gets with this hydrogen away. So you are coming to this. This OH gets one of the hydrogen on this, and you are coming to here. And compound B also exhibits optical isomerism. And they say compound B is exhibiting optical isomerism. So that is supposed to be our B. All right. So I'm gonna get here now. So I've already decided our B. So it's coming from, so this, therefore this is A. And addition of concave and heating, this OH gets rid of one of these hydrogen now getting here. And this has this optical active carbon. So this is my A and this is my B. when B is reacted with HBr. So we are adding HBr to B. So it is giving C. Hydrogen goes to here, hydrogen is I. Bromine joins to this middle carbon. So this is my C. Reacted with alcoholic KOH gives compound D and E. Alcoholic KOH, according to Zaitsev rule, hydrogen gets away from hydrogen is left, that is this hydrogen. So that you are getting a double bond here. When you are getting a double bond here, this side, red side, you have hydrogen and CH3. Then the blue side, you have hydrogen and again, sorry, you have this CH2, CH3 and CH. So that there are 6 strands. So that's why you have D and E. 2 groups one side, so that this is this. CH3 groups opposite, so that is shown. Then they say, part 4, both D and E when reacted separated with dill H2SO4. Dill H2SO4, addition of OH back, hydrogen goes to where hydrogen is high, that's to this carbon. Then OH is joining onto this red carbon. So you are coming back to same. All right. I want you guys to get here and show these 3 structures here. Addition of H2SO4. Show these 3 structures. This one, and this one. Those 3 purple color structures. The space is enough. Only these 2, don't go with A and B. I'm going to show that later. Finish. Then copy this. Somewhere you can find a place around. There are spaces around. Even the next page is there are spaces. If you go to the next page. Finish? Okay, now you have the taught complete knowledge. Now copy all these answers. A, B, C, D. These two can solve. They were not given enough information to go with these two. All right. D, E can be solved. Actually, D and E are position isomers. They are saying these two are isomers. They are position isomers. Then, moving on. Question number 33. State characteristic type of reaction that benzene undergoes, that is electrophilic substitution reaction. It's not there. First part. Okay, electrophilic substitution. You do not supposed to write this symbol. Don't write this one. This is the answer. Electrophilic substitution. That part is not in the single question. Then give the structure of the product and the mechanism for the reaction between benzene and this compound. So they are taking benzene and this. So whatever this this is the alkyl halide, this Friedel-Crafts alkylation. So this is the product. Just detach this chlorine and join that carbon onto benzene ring. So this is the product. Don't worry about any of these other parts around. We are only worried about this chlorine here. Okay, what happened is this chlorine is donating lone pair onto aluminum chloride. So here the chlorine, this is donating lone pair onto aluminum, so that this chlorine gets a plus charge, aluminum gets a minus charge. All right. So this is secondary alkyl halide. Either it can go with SN1 or SN2, because we know talking about the stability of secondary alkyl halide carbocation. We say primary carbocation unstable, so that going with SN2. Tertiary carbocation stable, so that going with SN1. So for the marking scheme, they accept if you are going together this, or if you are going like CH3 twice, CH plus. If this is without this, if this is only attacking If this is only plus charge is attacking onto this. That's also correct. Anyway, I have taken both together. So this chlorine is now unstable. So it is dragging always electron from this side. So that this next adjacent carbon gets plus charge. That is this carbon. So that this benzene ring is donating electrons onto this carbon. At the same time, this gets the benefit of getting this Cl1 breaking. So this plus charge is cancelling with this lone pair. So it is converting into AlCl4 minus. One breaks from here. It's joining onto this benzene. This is the hydrogen already is there. It is going through the resonance. Okay. This remember two different kinds of questions they are giving. Sometimes they are not talking anything about resonance. If they are not talking about resonance, I suppose you guys write these resonance structures here. And sometimes they are giving marks for these resonance, sometimes they are not giving marks for resonance. But we cannot get the width, so that my instruction is, if they were not talking resonance for the next part, usually they do talk about the resonance for the next part. For the next part is explain the stability of intermediate for this reaction. So we can just draw one of these intermediate, then stability means the plus charge is delocalizing through this resonance structure. Since they have asked this part, they are not giving marks twice. So they are giving marks here, so that even if you write the mechanism here, they are not giving marks here. So don't do that. But if they were not asking the same question later, then draw all these resonance. It would take just a couple of short minutes, maybe 1 minute if you are really, really fast. Anyway, so this is the first resonance structure we are drawing in this plus charge. Anyway, from this we can just show that this negative charge is attacking to this hydrogen. Hydrogen CH1 is polarizing towards this carbon. So this carbon is making back this one. So you are making this and plus this AlCl3. And also you can show this HCl as well. I'll write that again. Okay, then the later, but they are asking the stability. Just write that part later. For now, copy this, copy the mechanism and the product. Sometimes they are doing marks for these byproducts. So we better write everything, not for this question, but later now they are doing that. Finish. Okay, moving on to part 2. Let's write this. Form intermediate. Part 2. Form intermediate Part 3 actually, part 3, form intermediate, shows resonance stability, by delocalizing positive charge with benzene ring. Positive charge with benzene ring. By delocalizing positive charge with benzene ring. All right, show this. Okay, I need to start there. Just Peter. Ah. Because it is unmuted. Because unmuted with the screen. Here is not for both. Ah. In this body, it is too bright. I made it is not bright. It is a little dark actually. So I actually this brightness I got down because even it's on finish. Okay, the next one is asking if you do this photograph alkylation to benzaldehyde. What is benzaldehyde? Benzaldehyde is a compound with this CHO. Then this CHO group, this is the meta-director. So the normal reaction, but this time it's pointing or directing to the meta position. So this is the product. Then this is not necessary for your knowledge. That's why I'm using it. All right, question number 33 part B. A, B, and C are optically inactive. We don't know, we have to go in everything. Okay. Optically inactive, monosubstituted aromatic compounds with the molecular formula C10H14. Optically inactive, we have to avoid these optically active compounds. So if we go with these optically inactive compounds, I'm gonna go like this. Okay, we have to stick to these three. You can draw all. You can draw all optically active and optically inactive. If you go with this, you have to stick to only to these three structures which are optically inactive. So the middle carbon wall is supposed to have another two identical. So these three are the structures. C10H14 or like C10H14, or you can just go with this common formula that is saturated alcohols. So you can go with, you are not getting it. There's one thing is out of syllabus, otherwise we don't know these reactions as well. Then A reacts rapidly with concave Cl in the presence of anhydrous zinc chloride. That actually is sort of Lucas. Reacts rapidly means it's supposed to go through this tertiary carbocation. So that's supposed to be tertiary alcohol. Anyway, I don't know. So I'm adding zinc chloride concates here. This OH converted to Cl, OH to Cl, OH to Cl, and then which one is the tertiary? It's supposed to be A. So this is tertiary, so that I determine it's supposed to be A. B and C do not react with the same reagent as in appreciable rate. Okay, 10 minutes stability of reaction after 10 minutes is appreciable. It simply means B and C is supposed to have this primary part. So these both supposed to have primary part. So if you are getting more structure, then you can restrict, you can limit those structures only to this B and this one and this one, because you cannot go with this secondary. You have to go with this primary structure. B and C, when reacted with pyridinium fluorochromate, so BC, so again to this B and to C, I still don't know B and C. I'm adding PCC to these two. Gives compound D and E respectively. Okay, I don't know, Steve. I'm just going with this mild directly this, okay? This OH converted to CHO. This OH again converted to CHO. That's mild oxidizing agent. D undergoes aldol. In the presence of sodium hydroxide, while E does not. Okay, D-aldol means they are supposed to be, this is the alpha, this is the carbonyl carbon. So this is the alpha, this is the carbonyl, so that this is the alpha. On alpha carbon, there are two alpha hydrogen, but here on this carbon, there are no hydrogen. D only undergoes aldol. So this is D, so that this is B, so that this is supposed to be E, so that this is supposed to be C. So we already decided A, B, C, D, and E. Then moving on, part 2. B, when heated with concassous sulfur, gives F. So I'm going to B again, heating with concassous sulfur. This elimination reaction of water, converting this into this double bond, alkene. F reacted with HBr gives G. Then F with HBr, hydrogen goes to where hydrogen is high, bromine goes to the middle, so this is the product. So we came to G. G is reacting with alcoholic KOH. All right, alcoholic KOH. This bromine, see, you have to write all this, be brave and be alert. That's why some students are only getting 100 marks going to my plan. That's why see, some students are not going. So this carbon is the carbon with bromine, blue carbon, or green carbon. Both can give hydrogen. According to state group, major comes with this green one because that has less hydrogen. Hydrogen gets rid of the carbon with less hydrogen. So if you make double bond with this here, okay, I'm going back. Double bond here. This side you have hydrogen and CH3. This side you have this hydrogen and one hydrogen and this larger group. Each carbon has different groups. So it's supposed to have cis and trans. And if this hydrogen gets away, you can get double bond here. Then this becomes CH2, so that there is no cistron, and that is also the minus product. Is this clear? Before I moving on to here, I'm going here. So just underline this part. Anhydrous zinc chloride readily react with concave here. That is tertiary alcohol. Show that. BC do not, right there, it's primary. It's making primary. It's supposed to be a primary alcohol. Pyridinium chloroformate, PCC, mild oxidation. PCC, mild oxidation. And E does not react with sodium hydroxide, no alcohol. This is mild oxidation, PCC, mild oxidation. This is no alpha hydrogen. No alpha hydrogen. Yeah, rest of the part is PC. All right. Copy it. Where can we find this? No place. you may start little ahead of me. You have write all these, maybe it is optically active or maybe the compound which is not giving aldehyde, which is giving ketones while oxidation. Okay, as an example, if you go with this kind of a structure, you cannot go with this because this is giving this ketone on aldehyde with the and it's not with this EOH. Okay, these are the products, and I want you guys to write this little thing as well. All right, part 4. State whether G could exist in stereoisomers. Oops, sorry. There's this. See, this is G. G has this chiral carbon. Just show that. Show the chiral carbon on G. So let's write here. Here. Explain your answer. Carbon which connected to bromine is chiral which connected 4 different groups. Which connected 4 different groups. Question number 34. New questions, 2017 one. Okay. The alcohol, they are saying it's alcohol, A, B, C, and D are structural isomers of each other, having the molecular formula C5H12O. A, B, C show optical isomerism. So you are going with all these structures possible. Still, you don't know which one is A, B, C, or the one which is the other one. They are later coming to that D as well. D is not optically active. Okay, I'm just going here. Here, this is the explanation. A, B, C, and D, all these four alcohols. 3 of them are showing optical activity. Still, I don't know what is A, B, and C, but still, first time I'm going with this. One hydrogen, one carbon, 2 carbon CH2OH. Then this carbon, I'm detaching 1 hydrogen, 1 carbon OH. Then this carbon I'm joining here, 3 carbon. Then again, these 3 carbon, I can detach one of this carbon and I'm joining it to the other side. This is the chiral carbon. So I can make the structure. Or without chiral, I'm going like this. Without chiral, I'm going like this. 2 carbon, 2 carbon. Okay, these are my 4 initial structures. Could you draw any other than this? Okay. Then this exactly is my D. This is D. These 3, I still don't know anything about these 3. So I'm going with these 3, whatever they are saying. When BCG, okay, still BCG are reacting with potassium diformate. I know nothing. So I'm going to go with this potassium diformate is this. This is the potassium diformate. XYZ. Okay, we don't know what is what, but B gives X, C gives Y, D gives Z. Anyway, I still don't know that, so I'm just oxidizing CH2OH, COOH. This OH gets away with this hydrogen, that's a ketone. This OH with this hydrogen, that's again this ketonic part. And this OH getting away with this hydrogen, OH and H, that's again ketone. All right, I don't know other than that. I'm just drawing, okay? Then the products XYZ can be converted back to BCD respectively with sodium borohydride. All right, sodium borohydride. This reduces, this does not reduce it. Sodium borohydride, you cannot convert this back. It can reduce only aldehydes, ketones, or acetate, right? It simply means these 3, this is D, we already know. B, C, D are going through these 3 reactions. A is not converting back to this by sodium borohydride, so that this is supposed to be A. Is that clear? Because D already got, but they are doing all these oxidation for BCG. then we can separate B and C from A because A is making COOH, which we cannot oxidize to carboxylic acid back. Reduce to you cannot reduce this back to this by sodium chloride. All right. Then we came to, we already know this one A, this is D, then B and C. We still have to go with what is B, what is C, we don't know that. D, from D is coming. That's again there. So we can separate A. On here it is concatenation. So A and B gives E and F. So A gives E, B gives F with concatenation. That with concatenation, these are giving these alkenes. Okay, it's a removal of water. Still, we have no idea what is B and what is C. So I'm just going to go with all these three. Addition of H2SO4 is giving this OH, gets rid of this hydrogen, double bond here. This OH with this hydrogen, double bond here. I'm just drawing it with this same structure because it's easy for me to understand. Then this OH gets away with this hydrogen. So you're making double bond here. And this, you can just go whatever the way. So they are asking about AB is giving EF respectively, while C and G give the same product G. They say whatever two compounds are giving same product. If you analyze, if you go with this, and if you just go with the straight chain of this, if you draw this way, these two are same. So that this is G. G is coming from C and D. We already know G. So that my next conclusion is supposed to be C. If this is C, then next this is supposed to be B. Clear that? See how mindfully you're supposed to go. G shows diastereoisomerism, that is geometric, that's cis trans. Yeah. G have cis trans. All three compounds E, F, G. E, F, and these two both are G. From the same molecular formula C5H2, that's true. Initially, same item. When E and F are reacted with HBr, now I'm going only with E and F. Reacting with HBr, so you are adding with the Marconi flow, this double bond you are adding HBr here and here. H and B are here. So these two are the products. Same product, H is formed. See, this is the product, and also this is the product. If you write it as just the long chain, you are coming to here and here. 2 carbon has methyl, 2 carbon has bromine. Both are exactly the same. Is this clear? This is how you're supposed to go, but before that, I will bring you guys here. Okay, first show this. Let's show this. I'm showing reagent as well. And here we are adding HBr. Here, H2SO4 heating. Here, H plus oxidation. K2Cr2 excited. No. Sorry, this is wrong. X, Y, Z. X, Y, Z. B, C, D, we have to do this, right? I got that. Correct. All right. Then I want you guys to copy it. Can you read this? Is it too small? No. Copy. I'm showing that this I can drag from the thingy. This to this to this, and Z to Z, back with NaBH4. What do we do for this one? Observing field. And we can also write here, if you add NaBH4 here, no reaction. No reaction. It's not clear to read visually. Below, how come you're not coming physically now? Almost all these developers are coming physically. Good interaction, solving problems, discussing things with me. You are shaping up your life. And do you guys know, once you leave, only very rarely, very little couple of students are coming back to me and having these connections. Because you are going with your life. When you are with me, get the most, get everything. And I don't have time for you once you're done it at once, because I have to concentrate on new students. Same way that I'm doing to you. Even these students are like, they're asking different questions. They want to contact, like they're like, ma'am, could you give me a free time to talk? I'm not giving that to these past students, but whenever you guys are asking me, I'm giving time to you, because you guys are my priority. They already shaped up their life, their future, so I'm not worrying about them. If they are in critical condition, then I would call, I would support them. Otherwise, I let them to be independent. Finish. All right, then copy all these answers. Final question? Done. You did this question at home? Seriously, you didn't do this question at home? You're not improving then. Thank you. Finish. Finish. All right, moving into the next part of that question. They want us to go with this series. So this first one. So this, you have this board and it's still here. To both these NH2, you are adding, this is aliphatic NH2, this is aromatic NH2, and this is aliphatic. If the temperature is less, aliphatic is unstable, so you are converting this NH2 to OH, and this is aromatic, you are converting this to diazonic. Okay, so this is the product. Then this is your J. To that J, you are adding this. This is the through this electrophilic. Okay, to this one. This chlorine gets there with this hydrogen here. Then you are joining this nitrogen onto this phenol carbon. With respect to phenol, this is electrophilic substitution. So that you're going to get this product. But at the same time, whatever the group joining, just let it be there. This group is the blue group. This blue group, just let it be there. It's not involved in whatever the reactions you are going on. So whenever they are doing something like that, maybe it has this fourth para, but still already confirmed, already fixed. And then this is K. All right. Then they are asking L. Okay, whatever you are adding here, chlorine connects to OH. So that's supposed to be aqueous, any of these reagents. Either you can write aqueous sodium hydroxide, aqueous potassium hydroxide, just OH minus, or even water is enough. They have good mark even for water as well. Then you are here now. Then CH2OH to CHO, primary alcohol oxidation to aldehyde only by PCC, only by PC. This is all syllabus. To that, we are adding HCl. So this COH, and we have benzene. To this, we are adding this HCl. So what happened is, CN, the top here, CO bond polarizing here, hydrogen gets there. So you are joining CN, oxygen becomes OH. So CN, that's double bonded oxygen become OH. So this is a sign of hydrogen compound. Clear that? And at the same time, let me explain these three again. They are amplifying these three reactions. So the reaction one is with respect to phenol, this hydrogen gets away, this diazonium is joining here, that's electrophilic substitution. Then the second reaction, reaction number 2, chlorine gets away or is joined, nucleophilic, one gets away, one comes in, substitution, nucleophilic substitution. Here, H4, so you are attacking by a nucleophile, so it's nucleophilic. This double bond is breaking, so it's nucleophilic addition. Go with my summary notes again. See how it is the right thing. See, okay, hang on. I'm gonna make you going 100% with marking if you are doing full papers. Then I'm giving marks for these answers. Here I'm just showing. If you are not showing this plus and minus, deduce 2 marks. Deduce 2 marks. Deduct 2 marks. Deduct 2 marks if you are not writing plus and minus. If you are writing here N2, not writing showing these double bonds, then again deduct 2 marks. All right, so concentrate on those here. All right, complete the answer. Only part after part B. Finish? All right, then part C. So the reaction type is electrophilic addition. It's going to be just the Marconi industrial easy, hydrogen is 2, where hydrogen is 5. So this is a major product. Then they want us to show this mechanism. Again, go to this more stable. So this gets the plus charge, that's why bromine gets there. This is already polarized. So this double bond is attaching onto this hydrogen. Br minus gets away. Negative charge, you have to join. This is how they have given marks in. 1 mark to this arrow, 1 mark to this arrow, 1 mark to this arrow, and 3 marks for this product, 3 marks for this product. Even they have given 3 marks here, again they are giving 3 marks for this. I'm checking the answer if you already done. Sinhala, your next question, it is number 1. 1. All right, let me go to the break then. That okay, let's go to the break. It's almost 11. Yeah, it's 11 on my phone. Okay, get the break. 15 minutes break. Get this is your break. Get 15 minutes. Yeah. I said this is what okay, come back at 11:15. So they make all these, the name and not making the idea. Different kinds of accounting, different kinds of pay. Okay, we are done with question number whatever. We are moving on to question number 1 again. Under which conditions and how does bromine react with benzene? Okay, bromine, there are two different kinds of reactions that we know. Normal, this electrophilic addition and also this, electrophilic substitution and also this addition reaction. So let's write these two. Two different kinds of reactions. Two different kinds of reactions. Number 1, addition of Br2, in the presence of sunlight. In the presence of sunlight. This loses aromaticity of benzene. This loses aromaticity of benzene. Show this, we are making this hexabromocyclohexane. Next point, number 2. Substitution of Br2 in the presence of FeBr3 catalyst. In the presence of FeBr3 catalyst, with the brackets, electrophilic substitution. Electrophilic substitution. So it is. Again, we are going to back this order these easy questions. This is neutral. Organic compound name is this. Neutral means it cannot have this. Let's say it cannot have this carboxylic acid maybe. CSHYOZ 55% for 55 of carbon. It does not decolorize bromine water, so it does not have double or triple bond, not unsaturated, and also does not produce the precipitate with radius. It simply means there are no. Okay, here no unsaturation, here no carbonyl. With this not reaction with 2,4 DNP. What's the most possible molecular formula is asking? So the molar mass is given as relative atomic mass is given as 88. Carbon mass of A, so that's supposed to be 400. It's 58.55. Then how many is in 88? That's if we divide that by 12, we can get number of atoms of carbon, that's 4. Then we can write C4H-Y-O-Z. Then Y plus Z. These two we don't know. So Y I'm just writing hydrogen 1 into Y. Oxygen molar mass is 16. So 16Z equals 88 minus. This is this mass equals 48. So I subtract 48. That is 40. Then I'm going to go with this trial and error, which is possible. So if Z is 1, Y becomes 24. Hydrogen cannot be greater than 0.2 is 8 plus 2, maximum supposed to be 10. So if Z is 2, hydrogen number is 8. If Z becomes 3, then Y becomes 40 minus 48, that is minus 8. That is not possible again. So these two are not possible. So we have to stick only to this 8 when Z is 2. So that the molecular formula is C4H8O2. Empirical formula, you can divide this by 2 to get this common 2, factor 2. So then the empirical formula becomes C2H4O. All the possible structures. So C2H4O2, we can go with CnH2NO2, carboxylic acids and esters. Neutral maybe it doesn't have plus or minus charges. So you have to go with all the carboxylic acids and esters. Again, it's easy. Long chain. One carbon I detach. This one. Then from here, I detach one carbon joining here, ester, and detaching one carbon from here, detaching the other carbon from here. We are moving on. And I'm going back to this 3 carbon. So I can detach one carbon and join here. Then this is the fixed structure. Let me check if there is another one that I clear. Yeah, we had to go with this single one. This explanation is also better. All right. See, they are saying this is neutral. So these are acidic, but these are neutral. So we are only going with these. Well, we are not going with these two. Clear that? Okay. Copy here. Just right there. Carbon mass of A. Carbon mass of A. Carbon mass of A. Then carbon atom of A. Here, not possible. Finish what? Okay, then naming. Anyway, I'm going to give you all the names. Just write all the names. This is for you practice. And 1, 2, 3, 4, 4 carbon butanoic acid. Then second place, 2 methyl propanoic acid. Then 1 methyl propanoate, ethyl ethanoate. This one, propyl methanoate, and this one, 1 methyl ethyl methanoate. But this one is not actually necessary with or without that also right. Right. Probably with, 1 methyl ethyl methanoate. Give the necessary reagents and conditions to do color conversions. Okay, A, B, C, D. A, B, C. Now you remember these, we did even short now. CHOH, you can write whatever is any oxidizing agent. I am going to PCC because they are meant to be ketone. Oxidizing to ketone, you can get any of these are possible. Then removal of this CO, converting it to CH2, that is sigma concave CO, that is Clemens reduction. Then to that, to para position, you are joining to NO2, that benzene nitration combined with sulfuric 50 degrees Celsius. Then you are oxidizing this part COOH, any strong oxidizing agent. For A, all these are also possible. Okay. Ah, no, hang on. Can we use this? Can we use this? No. This is acetophenone. Acetophenone. Once you make this, is oxidized to this. So we cannot do or use any of these. All right, copy up here, then let's write this. I'll make it right. Okay, any of, just write down there. I'm just saying this point. Any of strong oxidizing agent, any of strong oxidizing agent, such as, copy this, acetic potassium permanganate or acidic potassium bicarbonate, acidic potassium permanganate or acidic potassium bicarbonate cannot be used, since it converts, since it can just write since this COCH3 converts into just of this benzene ring COOH. Question number 3. State the products of each of the following reaction with necessary conditions. Okay, there is no reaction between just gel H2SO4 and this alcohol. So the reaction is supposed to go with this conc H2SO4 170. I'm just giving you guys the knowledge. Whatever we are writing for now, at that time maybe they were writing this just conc H2SO4. For now, if you are writing this supposed to be, they were just writing H2SO4, but now we are writing conc H2SO4 170. Or either we can use anhydrous aluminum chloride and heating, or even P2O5, or even H3PO4. So the product products are wrong. I have got this single one again. So the product becomes this double bonded comes with the double one. Okay, then you are getting with this, so you are getting this is your A. I'm just writing this expandable structure. This is expanded structure. Then to this one you are getting B. From B, product. This is they are not showing this. Yeah. In your one, do you have the PCC here? Is it written? PCC? Yeah, my one doesn't have that side. So with the PCC, that again, this is secondary, and that is this compound here. This part is oxidized into COCH3. Secondary alcohol, regardless mild or strong oxidizing agent, they are going to this ketone. Then the third one, they are talking about this nitration of nitrobenzene, conc nitric, conc sulfuric 50. And since this is a meta-reactor, this is going to meta-position. So strong ring reactivator, meta-reactor. All right, copy this. Could you read this? It's not necessary to draw these reagents. These are just reagents. Same 1, 2, 3. I'm again showing expanded structure. These are the reagents I have written again, and these A, B, C are the answers. Let me show the answers. Let me answer. If I go with the, let me go in the English Sinhala one is more clear. See the Sinhala one. Only the answer is there, that's more clear, I guess. A, B, and C, A, B, and C. Okay, then if the product is A1, that is this, and to show isomerism, give you ideas. This has show this double one. Just highlight the double one, and here highlight this C. I have highlighted. You don't see the orange color. Okay. Highlight this double one and this hydrocarbon. Just write A cis trans, within bracket, stereoisomerism, arrow, diastereomerism, arrow, geometric isomerism. B, optical isomerism, within bracket, stereoisomerism, enantiomerism, enantiomerism. Okay, showing the structure, whatever the differences. This is we can show in one side two hydrogen cis, opposite side hydrogen trans. This is again you are showing just to show this. This is the chiral carbon. When you are drawing the chiral carbon, chiral center is just not changing. See, this distance same. And this C6H5, this distance and this distance is exactly same. But here, this hydrogen is supposed to get closer. And this, whatever the group, supposed to get away. See, the same distance. From here to here, same distance. All right, copy these two. Then I'm going to read it from it has grown. It was really? Yeah. It is cool. Yeah. How come? You were outside? Outside. Did they blame you like? No, seriously, like how All right, question number, moving on to question number 3, we are done. Moving to question number 4. An organic compound named R contains carbon, hydrogen, and oxygen only when R is burnt completely. CO2 and H2O equal moles. 1:1 ratio, or we can write X is to X. When 5.8 grams of R, so the initial mass is 5.8, water 5.4 grams. From that, we can find number of moles. Okay, I'm going to run this one again. All right. They are giving the mass of water. Mass divided by monomass. We can get number of moles of water 0.3. 5.4 divided by 18 is 0.3. Since this ratio is 1:1, then carbon dioxide moles supposed to be the same. The number of moles of water is 0.3. Number of moles of carbon dioxide is also 0.3. Then what is the mass of hydrogen? So H2O 0.3. One water has 2 hydrogen. So the number of moles of hydrogen become 0.3 into 2. If we multiply mass by molar mass of hydrogen, not H2, molar mass of hydrogen, we can get mass of hydrogen. Molar mass of hydrogen is 1. So that mass of hydrogen is 0.6. So now we know mass of also we can, so this is the mass of hydrogen. Okay, so the number of moles of carbon dioxide is this. Carbon dioxide has 1 carbon, so that number of moles of carbon is still the same. If we multiply that moles by the molar mass, that is 12, then we can get mass of carbon. So that mass of carbon is 3.6, but the total mass is 5.8. If we subtract this is supposed to be 5.8. Let me check. Let me check. If we subtract other two from, because initially it's taken 5.8. Subtract other two from that, we can get the mass of oxygen. So that 3.6, 0.6, 1.6 mass ratio divided by 12, 1 and 16 to get more ratio. Then this is the empirical formula. Then they say R, which has only one functional group. They say it has only one functional group. Gives an orange red precipitate with 2 for DNP. It has only one oxygen for this empirical formula. One functional group with 2 for DNP, that's supposed to be this ketone group. One functional group supposed to have one ketone group. So that one oxygen supposed to be there for the molecular formula. So the molecular formula is still C3H6. So, all right. Okay, done. Yeah, this is a good method. This total mass, this is the printing error, this is 5.8. Okay, then just write the answer for this part. 2 for DNP Brady, only one functional group. If you have written, that's all right. Otherwise, 2 for DNP, that is Brady. One functional group, which is this. Functional group, which is this. Then the answer. R reacts with the hydrogen cyanide. The component is formed with a chiral carbon. Okay, what are the possibilities? There are two different possibilities. Two isomers we can draw for this compound. So this is aldehyde and this is ketone. If you go with ketone, so already you have these two identical. So this is not giving chiral. To get chiral, you need to have. How do you get chiral? This oxygen become OH, then you are joining CN here. One group, two group, three group, four group. This is become chiral. So just show this. Show these two are possible. R can be aldehyde or ketone. R can be aldehyde or ketone. Okay, then the answer. Nucleophilic addition reaction. Oh. මට project technician කෙනෙක් කතා කරනවා. ඒ machine එකේ පැඩල් එක ගැප් වෙලා ගියා. එයා බයික් එකේ. මාකර කාලේ කැඩිලා. මම දැන් lecture එකක ඉන්නේ. මම yeah මම okay. They are not following anything with each other. One is the second. Okay. Part B, draw the structures of major products of Flavin reaction. So this is a Friedel-Crafts ethylation. Just a Friedel-Crafts ethylation. This is the product. Just write there Friedel-Crafts ethylation. Then RNH2, 1 mole of this. So this is 1 mole. So you're going to stop from here. So that is become this primary amine with 1 mole of this. So you are going to the secondary amine. This is the product. Third one I have written because third one was out of syllabus. Section no 2. Not talking about this temperature whatsoever. So it's OH. Copy these two. The answer. I'm finished. All right, so the next part, question number, yeah. Converting this CO to CH2, that's Clemmensen reduction, zinc mercury concave Cl. Then the next one, the product is OCO. What is this? This is an ester. Very good. This is an ester. So this sodium has to get away. The ester part has to join. Either you can go with this carboxylic acid or with this acid halide. This chlorine gets away with this sodium, or this OH gets away with this sodium. But if you are using acid halide, you can just write this. But if you are using this, either you have to go with this concentrated sulfur or heat into the 80 degrees Celsius. So there are three answers for the second one, this one, or this one, or this one. Copy up to that. And check your answers if you're done. Okay, draw the structure of made a product following this is okay, if you're not done unit 14, you will know the answer, but we did this for when we became this spider diagrams. I have given this in the only in the spider diagram we have that. So this is the phenol formaldehyde. So these hydrogens are getting away with this hydrogen. Sorry, this CO is getting away with this hydrogen. So on the other side you have another phenol and this hydrogen again getting away. COH2 this. Then you have this C, this you are making this one, CH2 one there. This oxygen gets away with this hydrogen and the hydrogen from the other one. So this is the product that we did for unit 40 of this. This is the bakelite, production of bakelite, or we call it phenol formaldehyde. This is a thermoset polymer, bakelite, thermoset polymer. Just give me a second. See, it's here. Everything is showing here. This is how it is going to be confirmed. This. Next part, this is reaction between this Grignard and carboxylic acid. Here, if they have given this acid halide or any carbonyl compound, that gives a different reaction. But what happens here is carboxylic acid just acting as this proton donor. This Hydrogen gets away with this R group, making this RH. Then this oxygen is joining onto this magnet. So you are making CH3COO-MgX. So these are the products. Just right there, Grignard acts as proton acceptor. Grignard acts as proton acceptor. Okay, so the given compound is part D, C9H2O2, and they say it decolorizes bromine water. Just underline that and write there unsaturated carbons, which dissolve in diluted sodium carbonate. Just underline that diluted sodium carbonate, carboxylic acid, ortho and para-nitrophenol, carboxylic acid, ortho and para-nitrophenol, and quaternary ammonium salts. Quaternary ammonium salts. All right. Anyway, so the unsaturation is really high. C9H8, highly unsaturated, not like the alkene. So I have to subtract C6H5. So that I'm getting this structure. Remaining part becomes C3H3O2. 2 oxygen, that can be carboxylic acid or maybe an ester. But ester does not react with sodium carbonate. So this definitely supposed to be, there are no nitrogen, so it cannot be ammonium salt or nitrophenol. It cannot be any of these nitrophenol or quaternary ammonium salt. Since it's reacting with sodium carbonate, it's supposed to be carboxylic acid. So I have no idea whatsoever. I'm just drawing benzene. So remaining part I'm just studying carbon, 3 carbon, then 2O oxygen supposed to be carboxylic acid. So I'm just getting this part as carboxylic acid. Then remaining hydrogen, 3 hydrogen. And since we're supposed to have this bromine decolorization, we are supposed to be this double bond. You cannot keep double bond here. You cannot make a double bond here. Then this carbon going to have 5 bonds around. So that I'm putting the double bond here. Then I have only 3 more hydrogen, 1, 2, and 3. So if I come up with the very first structure, going on with the second, third are easier. Then I'm changing the COOH group onto this carbon. This is just normal path you can go. Other than that, you cannot draw any other mono substituted, but you can change the COOH. You have to keep the COOH. Then you have to separate the CH double bond CH2, so that you can go with ortho, meta, and para. Just copy this little thing. Highly unsaturated. Highly unsaturated. Highly unsaturated. Two oxygen, no nitrogen. So that COOH. So that COOH. All right, copy this one. Finish one. Okay, easy. How do these conversions that you're asking? The very first one. Any of these other than tertiary carbonyl carbocation, COOH, any of these strong oxidizing agents, you can add any of these. Then this COOH, carboxylic acid, ester, alcohol with concatenation sulfur or H-Celsius. Again, this group to this. Any of these strong oxidizing agents. This is para director. Sorry, this is a meta director. COOH is meta. Then nitric sulfuric and 50 degrees Celsius to meta. CH3 I am this. That iodine gets away with one of these hydrogens. This CH3 is joining onto this NH. And it can go up to this removal of all these hydrogens. So it is joining in benzene ring. H2 converts to this nitrogen gets away with 2 hydrogens. Then another next one is going away with this lone pair. Then you can join 3 CH3 groups. Since this is getting plus charge, it is existing as I-. Is that clear, this one? It's going with this quaternary ammonium salt. This time with iodine. Quaternary ammonium iodine. Okay, copy these 3. Finish. All right, then, okay. The question is asking, see, I told you just you are stopping whatever the question they are asking. Write the mechanism to get to this CCl4 plus 4HCl, but you are not showing all the parts. See, this is how we are showing. This is how they are getting marks for according to the marking scale. So you are showing this initiation step, homologic cleavage, half arrows, 2 free radicals. Then you are showing the first step. You are only showing the first step. Homologic, it's making this CH3 free radical and Cl, and this propagation, CH3 free radical is attached onto this chlorine to get here. Then same way, same reactions going on until you get this final product. And chlorine free radical, these two together goes to the termination. Okay, that. So you are only drawing up to that. So this. Moving on to part C. Again, state the structures of major products. So this is meta-director NO2, but still just the normal nitration. So to NO2 to meta position. Anhydrous aluminum chloride, acetyl chloride is this, CH3COCl. This is also para. So you can get two products, O2 and para. Just you have to draw both. Next one, magnesium triether. They are not adding water here, only magnesium triether. So Cl joins with magnesium. You are making it green art. To that you are adding this ethanol, methanol. Methanol only acting proton donor. That MgCl gets away with this OCH3, and this hydrogen is joining onto this carbon. So this hydrogen is joining here. So this is become CH3O MgCl, CH3O MgCl. They are not requesting this part, but they want this part. But for our practice, let's write this as well. All right, copy this thing. Finish. Okay, that's all for question number 39. Going into question number, question number 7. 6 is done. Again, these regions are, it doesn't work in Sinhala, it's clearer, and there are no English just involving. COCH3, that is Friedel-Crafts ethylation. Reagent supposed to be this COCH3 supposed to join with this chlorine. Then CH3COCl supposed to go with anhydrous aluminum chloride. Then this is just the bromine water because it has this tribroma, which is a bright color. This is phenol identification step. Reaction type is electrophilic substitution. Copy the first part. Okay. Benzene nitration, intermediate, you know that benzene, this attacking onto this NO2 group. I'm not going with these mechanisms I get, and I believe you guys know them well. Nitric sulfuric reacts together, hydrogen coming from H2SO4 protonate this HNO3 to release NO2 gas. So the reaction type is electrophilic substitution. They want us to write this intermediate. Either this or any of these are accepted. They're accepting all of this. Okay, let's copy this part only. Finish. All right. Again, they are asking the major product. So this is 2 for DNP. This is actually again this imine formation between these two hydrogen and this oxygen. So you are just joining this carbon onto this nitrogen. So I'm just joining this CH, benzene CH, this part. To that, I'm joining this nitrogen. To that, I'm joining this NH benzene with 2 nitro groups. That is this whole part. They are saying this alkaline. In alkaline medium, this is not necessary, but you have to go with this negative. It is the salt. And this again P2O5. This is dehydration of amide to nitrite. All right. Check these two properties. Finish. Question number 8. This is I have just shown this here. See, this is the nitration that we did earlier, acting as the acid and base, and protonated this oxygen, unstable. This is breaking from here, giving this NO2. That NO2 part is attacking onto benzene ring. Just refreshment. Then question number 8. Indicate okay, phenol esterified only with this is the ester part they are showing. CHO is just existing additive. This is an ester, esterification of phenol only with acid halide with phenol. Okay, you don't want extra driving forces for the reaction. If you add this aluminum chloride, then it goes with what? Purified air separation. So far, this reaction is only going with this CH3CO3L. And this is diazone. See, they can give this diazone without charger, but we cannot do that. Just diazonium, sodium nitrate HCl, temperature is supposed to be less than 5. And to get green bromine, Sunday reactions, UBr, HBr. Copy these two. Be alert. Okay, right. Be alert. Don't get sleepy. You are deciding your life. If you're having this continuous sleepiness, just talk to your parents and do something. Something wrong with you. I don't know, maybe your health or something like that. Again, same thing they are asking. Since we need to complete the note, we are just writing this. Okay, part B, just this same reaction they are asking. Initiation, couple of propagation, And this time they want us to limit to this compound, so we can just come up there easily. 1 chlorine. See, all these are really, really easy. Just I'm doing this for you to get the practice. Finish. This time they are asking about the Spirocraft acylation. So the reaction type is electrophilic substitution. Electrophile is this RCO plus. How do you get that? This chlorine is donating electron onto this aluminium. Chlorine gets a plus charge. Aluminium gets a minus charge. But this from this RCO, this plus charge coming onto this is getting here and this is joining onto there. The plus charge coming onto this carbon is stable. Either you can write this together or you can write this separately. And it is attacking onto benzene going through this acylation. And this is the product intermediate. So you can draw with any of these. That's why I have written here all. We are not writing all for the exam. For now, for the practice, you can write everything. Even the resonance fibrillary is acceptable. Moving little by little onto this modern chemistry again. All right, then initially you have one group, so you are adding another. The only part to consider is this is meta director, so the second one is going on to meta position. This is the answer. So they are talking about the acetophenone. This is the acetophenone that you already know. And this COCH is a mild ring deactivator methyl. Just write that. Mild ring deactivator methyl acetophenone, the COCH group. I'm not talking to any of the students online right now. You are hearing me say, calling your names. But I believe you guys are very concentrating on what you are doing. If you have this good inspiration, you are not getting sleepy. Just think that whenever you are watching a movie or whenever you are going these trips or whatsoever, when you are doing something entertaining, you are not getting sleepy. So have that inspiration. This is deciding your life. Never forget that. I'm not boasting, but I'm having this fun, entertaining, full of excitement this life. I guess part of that came through my education. So be like that. Be like that. Don't get sleepy. That is my request. Write the structural formula of the organic compound of the chlorine. This is the final product. And so that's gotten by whatever this. with something, heating with sodium hydroxide, so that this is aldol, and before this, let's say the compound is supposed to be this. Okay, this is more stable, so I'm joining OH here. So this is the compound before this. This compound came through what and what. So this CH2CHO is this, and the rest of the part is this. So this acting, the blue part is acting as the carbonate. If I write the equation, the mechanism, this is the benzene ring, COH. Then the red part, that is CH2COH. This negative charge on this is the nucleophile, red nucleophile attacking to blue carbonyl. Then the bond forms here is the bond I'm showing here, and that is this one. Okay. Then alpha beta unsaturation is there, so you are going there when you heat. So this is the other product. Then the next one is ether. You have this alkyl halide, the other part supposed to be this, or whatever this O part, and that comes with this benzene ring, supposed to be this sodium CH. Clear? All right. Whatever you want to, you're supposed to write, just copy down. This is showing some little extra this information. See, this is the if you go with this self condensation, this is showing how you are making this nucleophile. This OH minus is getting one of this hydrogen at H plus. This one is polarizing towards this CH2, so you get a negative charge. That negative charge is attacking onto this. So you are coming to here, heating up, addition of water, then you are going here. Sodium phenoxide. All right, rest of the part. Okay, finally we are starting little conversions, moving on to more and more conversions there. Okay, when we come up to here, see how many questions we did just to remind you guys these organic equations, organic reactions that we did. I could skip those. That's why, you know, some students are not getting enough knowledge. Even if you are, like, let's say you are at home, you are studying real, then you don't want these equations. But to remember, to memorize everything, and you know, the majority of students, I believe they are not studying enough. That's why through this path, they are showing this higher effectiveness, whether you study at home or not. You are memorizing things when you are doing these questions. Little by little, now we are moving on to conversion. Conversion is going to be really easier for you now because you are already familiar with this equation. I'm just keep asking you guys to do this because for me, I feel like some students are not still there. Remember, I told you that from all the students in 2023, I saw their talent. So I can get A classes from each of every single of you. Even a couple of students came to this, new students came to this calendar class. Even they are really something. And they can really compete with you because they are showing very good talents. We did this organic chemistry thing. 2 hours and 6 days, Sinhala. 2 hours and 6 days, they finished full organic chemistry that you did 1.5 3 months. And so together, I'm saying I want A classes from everybody. Okay, I'm not any excuses, and I will be so mad if you get this because we are in this camp, and from especially from the 2022 English medium students, showed very high progress. All right, so moving on to these conversions. Okay, the very first one. Initially, you have this NO2. Finally, you don't have this NO2, but you have this COOH. Either you have to find a way to convert this NO2 to COOH, otherwise you have to remove this NO2, then again joining some other groups to come to this COOH. But initially we know that we can convert this COOH. There are two different methods. If you have CN, addition of H3O plus, you are making COOH. Or otherwise, if you have this R group, addition of any strong oxidizing agent COOH, and also we can go with this Grignard to get COOH, that you know Grignard, let's say that you have bromine here in GBR, then it is to CO2 or to formaldehyde, okay, we can come back here. But since they have given NO2, the best way is to go in with this diazonium. Right? Then tin content here sodium hydroxide excess, you are converting this NO2 to NH2. That NH2 to diazonium with low temperature sodium hydroxide is here. Then convert it to CuCN, KCN, CN, acidify to COOH, or diazonium H3PO to benzene, add Friedel-Crafts alkylation CH3, oxidize into COOH. All right. Copy this, check this, right? Whatever the answer. Sinhala, what message it is? I'm going to do it. On that one. Yes, 31 more questions. I'm sorry, but she will go. You're going to do that Harmonian did now with one of the did everything in that. All right. How easy. Looking at this, see at that time, these are ancient questions. At that time, one of these final hydrogen is one of these interested. Okay. Whenever you see two active groups, two functional groups on one single carbon, that can come with final hydrogen. Then to the middle carbon, either CNOH, CN halogen, CnNH2, or even like this, double bonded carbon COOH, that the other group can be OH, halogen, or NH2. So any of these conditions are going with monohydrate. Copy this. The central atom. Cyanohydrate to central atom. Two conditions. This and this. Look at me here. Okay. So you need to join 3 carbon this part, then OH and CN come into the cyanohydrin. 3 carbon to get this OH. Cyanohydrin, to make the cyanohydrin, you need the carbon here. So you are going with the Friedel-Crafts acylation. Copy this. What is it? What is the question? You're not understanding. Finish. Explain how parametrophenol acts as stronger acid than phenol. Okay, the first one is phenol, second one is para-nitrophenol. They are not expecting you to write this resonance structure. Just need to explain these activities, electron attracting nature of NO2 plus, right? If you want to remember these two, let's write the answer. You know the answer, let's write. Phenol shows its acidity. Phenol shows its acidity through breaking this OH. OH bond to release H plus. O dash H bond to release H plus. But benzene ring pushes, its pi electron cloud towards oxygen on phenol, so that it's become harder, for hydrogen to leaving, comma, giving its 1 electrons to oxygen. But NO2 is the strongest ring deactivator. And drags benzene's pi electron clouds towards NO2 group. Next point. This helps to decrease electron density of oxygen. And so that easiness for hydrogen to leave as H plus increases. Therefore, show high acidity. Therefore, show high acidity when NO2 bonded phenol. Grammar is not exactly correct, that's what I said. When NO2 is bonded to phenol. All right, that's what it is. Again, this is the mechanism in asking. This is the electrophilic addition reaction. Just copy this down. We don't want explanation. We need this explanation. This is mechanism of alkene bromination, electrophilic addition. Just write that it's electrophilic addition. Electrophile is Br plus for Euroactive. Electrophilic addition. Br plus is electrophile. Br plus is electrophile. All right, the next part is asking when this compound, see, this is the normal condition, both carbon and all these hydrogen have same environment, but this is it's different. From this side, you have this inductive effect like this. Then this is make the more stable secondary carbon cation. And you are adding this IBR, bromine, iodine, electronegativity of bromine is high. So that bromine is supposed to get delta plus, iodine is supposed to get delta minus when you are drawing this. Secondary carbon more stable with inductive effect of CH3 group. And this is primary carbocation, this is less stable. Once you make the carbocation, then Br minus is just attacking onto that. Then you are making here middle bromine, terminal iodine. Here terminal bromine, which is less stable. So this is more stable for that. All right, moving on to, before moving on to writing part, just copy this. Time is running by bullets. When you look here and there, everything has already gone. All right. Let's write the explanation. Write this. Electronegativity. Copy this. Of bromine is greater than iodine. Therefore, IBR bond polarizes towards bromine. IBR bond polarizes towards bromine. Next line. Due to inductive effect, comma, CH3 group pushes its electrons. CH3 group pushes its electrons towards double bond. Towards double bond. Therefore, secondary carbocation is more stable. Therefore, secondary carbocation is more stable. Therefore, it attacks IBR bond. It attacks IBR bond and first joins iodine to terminal carbon. Therefore, it attacks IBR bond and first joins iodine to terminal carbon of the double bond. Terminal carbon of the double bond. Therefore, it becomes the major product. Therefore, it becomes the major product. Therefore, it becomes the major product. All right, no benzene stuff, but this is easy to go with. 1, 2, 3, 4, 5, 6. That's what they have taken. 5 bromo, 2 nitro. So here the compound is phenol. So phenol supposed to get number 1, 2, 3, 4, 5. Just copy it. Then the next one, pent. So I'm just drawing 1, 2, 3, 4, 5 carbon, oleic acid, COOH to the terminal, then the 2, second position methyl, fourth position OH. So this is the answer. That we already know, aryl halides do not participate S10. That's because this sp2 hybridization S character percentage is high, so it's electron negative. It's not giving its electron onto bromine to get away as Br minus. Second thing, when it's delocalizing electrons onto benzene ring, it gets this double bond nature. So it's not participating for Sn. Explain why this bromo group shows orthoparadirecting directing ability when bromo benzene is hydrated. But here what happened is this lone pair is donating here. Then this one of these pi bonding is polarizing towards this carbon. This carbon gets a negative charge. Since given electrons, bromine gets a plus charge. And these lone pair are donating onto this CBr. So it gets this double bond. So this is going along with the benzene ring. Finally, we are coming to here. See, negative here, negative here, negative here. So ortho and para positions are activating more electron density. So any electrophile attracts onto ortho and para. All right, that's right. Nitration is an electrophilic substitution reaction. Don't write SPA. Nitration is an electrophilic substitution reaction. Nitration is an electrophilic substitution reaction. NO2 plus is the electrophile. NO2 plus is the electrophile. NO2 plus is the electrophile. Therefore, there should be positions in bromobenzene. Therefore, there should be positions in bromobenzene with high electron density, for NO2 plus to attack. With high electron density for NO2 plus to attack. Now let's show these high electron density positions for the day. Show these double-headed arrows, it's a must. They are great marks for these. These two double-headed arrows are must, they are green marks. Okay, just continue. This clearly shows This clearly shows how L-O-N-E, okay, how lone pairs on bromine, delocalize with benzene ring, increasing electron density of ortho and para positions. Last point, therefore, NO2 plus can easily attack. Therefore, NO2 plus can easily attack to ortho and para positions. This way, bromobenzene shows ortho-para directivity. NO2 plus can easily attack to ortho and para positions. This way, bromobenzene shows ortho-para directivity. So we need to join these three bromine. The easiest way is to bromination of NH2. Strong in activator, so it's activating all these three positions at the same time. So you can join with these three. But here we have NH2 with chlorine. Easiest way is to join with this diazonium. So that converting this to tribromobenzene. Sodium nitrate is 5 degrees, less than 5 degrees Celsius diazonium. CuCl HCl condenses to properties. Okay. Okay, let's start from here. All right, these both are methanol. So we can go whatever we can. Nitric sulfuric NO2. Then Friedel-Crafts alkylation C chemistry. That CH3 convert oxidizing using potassium from permanganate to this one. But once you add this one, you cannot add this. You have to wait until it gets there. First you can join this, then join NO2. Or first NO2, and then this. So that's correct. If you want to record, you can't be able to get tomorrow because I have another 2 more classes today. So G, ඉවරයි. මේ බබලා දෙන්නත් එක්ක ගිහිල්ලා යාළුවෝ ඉස්සරහ යනවා. Okay. Okay, darling. Okay. Bye. Take care. Love you, everybody. Bye. I'm ending the meeting.